All right, so we're going to take a look at the scene where we're doing the sort of tangent spiral effect, just to sort of show you how to set it up. We've obviously examined the theory behind the effect and exactly how it's working mathematically, but let's take a look at how we can apply that in 3D. So I have my sort of cached character over here. I've cached it just because I wanted to sort of convert it and time shift it. So I've sort of cached it to keep it nice and light in our scene. Okay, so we've got a single frame of this character, and obviously I've got him like my object is rotating around. Okay, I'm calculating normals, and then here I'm scattering points on the surface. Okay. Now I almost always switch relax off. I don't know why it's on by default. Honestly, relaxing gear creates a very unnatural look, and it's really heavy, so I never have it on. But I'm scattering the 3,000 points, and that's all I'm really doing in here. Okay, so very basic. And then here I'm just creating some colors, right? So I'm taking my position, right? But I'm setting the y vector component to nothing, okay, to 0, right? Just as a way of kind of having these kind of like vertical streaks of color. And then I'm putting that into a noise, and that noise is being put through a ramp. So the noise is essentially trying to create like random values along a gradient, so 0 to 1. But then the ramp itself is determining the colors that will sort of vary between. Okay, and obviously if we wanted more green, for example, I would just put in another green sort of pin over here and move it so that there's more green on this, right? So it lets me just essentially create a random color. But then what I'm wanting to do afterwards is just fix it a little bit, because I want to make sure that the saturation is always the sort of maximum, right? Sorry, not saturation, the value. Okay, just because I was getting some depending on the color, it kind of it sort of dips and is a bit too dark. So no matter what color comes in, or even if it's totally random, what I do is I take the color, I'm converting from RGB to HSV. Okay, and ultimately we're trying to alter the V, so the third component. What goes in as a vector, what comes out as a vector, but coming in is, your 3 channels are red, green, and blue. What comes out is your 3 channels are hue, saturation, and value. So what we can do is alter the third vector component now. So when we go under set vector component, you'll see here under component 3, I'm just setting the value to 1. Okay, and then here I'm setting the value to component 2 to also to be 1. So essentially I've got a random hue, but the saturation and the value are both set to be maximum. So we've got very bright and very saturated colors, and then I'm converting back to RGB and writing that out as color. Okay, so just a way of creating kind of random colors, but no matter what I put in here is going to come out nice and bright and visible. And then I'm going to talk about this node now. Yeah, this is where all the maths is happening, but kind of coming into that as well is my collision object. So I have essentially my character, but merged with the ground as well underneath it, and I'm calculating normals. Now, the reason for this is because I need an object to essentially use as a collider, because as we're creating the swirl of or the spiral of this these arcs, these curves that sort of snake their way around this geometry, we obviously need to ray our points onto something. As we create a new position for the point, we need to move it back onto the surface all the time. And when it reaches the bottom, we actually want it to flay out and kind of like merge or join with the ground. So that's why I've actually included the ground as part of the collision object, because then when we get to the bottom, when we create a new point and we ray, it may actually ray onto the ground, which kind of creates a nice look at the bottom. Now, obviously, if you wanted to avoid that, then just don't include the ground in the collision object. Okay, so let's take a look at what's happening inside of this wrangle, because the wrangle node over here is essentially what's creating all of this work, right? So all of the spiraling that's happening here, you can see it like best on the arm. sort of all of that work that's happening. Everything is coming from literally, we've got a bunch of points that have colors, and then the wrangle is doing the rest. Okay, so let's dive inside of this and see what's happening. Okay. Now, obviously, this is not a super long, 8-week course on Vex. So if you guys do sort of want to understand Vex a lot more, then Rebelway does have a Vex course that I've created for them, which is all about Vex, and we're going to go deep into this stuff. So if you would like to understand more of that, then that is probably the course for you. Here I'm going to sort of just go through the basics of what we're doing. So I'm going to sort of assume that you understand at least a certain amount about Vex. Okay. This can be recreated in VOPs. It will be quite a setup in VOPs. Honestly, Vex is way easier. It's only a couple of lines. It's very simple and neat and easy to understand. In VOPs, this would be an absolute nightmare. I don't even want to think about what that would be like, but it can be done. So if you really do want to do it that way, you can. But if you are so good at creating crazy VOP networks, then you probably have the logic and understanding of this enough to convert it into Vex and rather do it in literally a couple of lines. I mean, we're talking about 24 lines of code, and it's much, much easier to manipulate than in VOPs. Okay. So here I'm just setting a couple of initial variables first. So I'm storing my point position in a variable called pos. And the reason is because I'm going to be altering this pos and eventually using it as the position where I want to add a new point to. And I don't want to alter the original position of my point. I just want to alter the position of the new point, but it's relative to the point position. So I'm starting with pos equals v at p. I'm also setting myself an up vector, which I like to set it in a variable because if I use it multiple times and then later I decide I want a different up, I can just come and change it in one location. And the up is so that our spiral happens, in a certain direction. Obviously, if we gave it, left and right or whatever, then it would spiral in a different kind of way. It would sort of rotate around a different axis. Then I have normals on my points because I had normals on my geometry, and the points inherit those normals, but I am re-normalizing it just to be certain, because we're going to be doing a lot of things here that expect the vectors to be normalized. So I always just like to normalize it here for myself. And because we normalize it before writing it into the variable, it means we don't have to normalize it every single time we reference it. So that's much easier. And then I'm creating an offset over here. So the offset is essentially just it's basically determining the shape of the spiral, because what we're doing is taking the point and then we move it along the tangent and then along the offset, and then that's the new position of the point. So because our offset has negative in y, it means that it moves down a little bit every frame. The higher this value is, so the more negative it is, then the further these spirals, so that the spirals will go less sort of round and will actually just go straighter, like further down. Okay. So I mean, I can even show you if you want. Let's take this to, well, let's double it. Okay. So multiply by 2 and you'll see that these spirals then go sort of much steeper down. Okay. So this might be the look you're after, but I kind of like the, I like it to spiral around quite a few times. It looks nicer. Right, so we'll let that just kind of recalculate itself. Okay, so those are my initial variables. Now, ultimately what I'm going to want to do, we're running over points here, so we are looping through our points already, but on each point I want to loop a certain number of times, and the number of times I'm looping is essentially the amount of points I'm creating in that spiral, right? So what I'm going to do is I'm creating an empty array. This is where I'm going to store all the point numbers of the points who should be joined in that one line. Because at the end, we're going to have just a collection of points, and then we're going to add them all together and join, essentially create those polylines. And when we do so, we don't want to get all the points confused between so let's say we've got point 0 on the surface here. It's going to have 200 more points created that are associated with itself, but so will point 1 and point 2. And so there's loads of points being created here. And we need a way to associate all of the points from point 0 that are forming its spiral in order to join them together. So I'm creating an empty array. And then I'm adding our current point number to that array first. Okay. So the only thing in this array at the moment is the original point. But then as we loop through and add all the extra points, excuse me, add all those extra points in the spiral, we will append them to that array so that at the end, we just loop through that whole array and essentially add a polyline. Okay, so I'm creating a for loop. My index is starting at 0. So I'm initializing my index, and then I'm saying that if we'll stop looping when I is less than the number of, we'll continue to loop while the I is less than the number of iterations, which is a parameter I have set. So I'm saying loop 200 times. That's essentially what I'm saying here. And every time we loop, we increment our iteration by 1. So that's what I++ does. Okay. So all of this basically says loop 200 times. Okay, but I can control here how many times we loop. Right? So if I want to, we can go loop only 20 times, and then that's going to calculate obviously a little bit faster. And we could calculate, only 2 times. And so every time we loop, you'll see that the spiral grows longer and longer. I mean, you could even animate this value if you wanted, so it keeps looping and spinning all the way around. Okay. So let's set it back to something like 50. Okay. Now inside of that loop, all I'm essentially doing, I mean, we discussed this theoretically already. We want to offset along the tangent, offset along the offset vector, create a point there, ray it back onto the surface, and then move on. So that's all we're doing here. We're calculating the tangent based on the normal. Okay. So we're doing the cross product, which is exactly what we were talking about here. Taking our normal and our up, which are both normalized vectors. Okay. And we are calculating the cross product. Now the result is the tangent, but the tangent also needs to be normalized. So I'm normalizing it again once we get that back, right? And then I'm multiplying by my own float here, which is just a distance, because I'm ultimately saying, okay, move along the tangent in terms of a direction, but I want to tell you how far along that tangent to move. This will ultimately be essentially a scale of how shallow these spirals are as well. Yes, our offset has a big part to play in that. So this is how much is being offset downwards per iteration. But this distance is also saying how far to the left or right it goes, depending on the direction of the tangent. So we kind of, these two are going to determine the shallowness of our spirals. And then we're taking our pos, which remember is our point position, and we're adding the tangent and we're adding the offset to it. Okay, so we're overriding the position values by a new position that has the tangent and offset added to it. Now this is going to be the new position of our next point, but also because we're looping and we've stored it in a variable, the next time we loop, pos will no longer be equal to v at p. It will be equal to the last position that our previous point was. And that's how we create this kind of spiral, because each point is not starting from the original point, but starting from the point prior to it. So point 3 is looking at where point 2 was, calculating point 2's sort of original position, and then calculating the tangent, the offset, or whatever, and doing the whole thing again. And then point 4 will then look at where point 3 left off. And so that's why we end up with this kind of line that's drawn instead of everything just being centered around the first point. So once we've calculated that new position, it's floating in space. We were on the surface because we started with a point that was scattered on the surface, but we've now moved along a tangent and an offset. So we could theoretically just be in midair over here. So what we want to do is move it back to the surface. Okay. So this whole step over here is all about doing that. This is essentially the way that we do array SOP, but just in vex. So we store a hit prim and a hit prim UV. So we initialize these two variables. We don't have to actually have any values for them because we're going to be writing into them. And then we run an XYZ dist function, which is essentially just array to minimum distance. We point at 1, which is our second input. So that was our actual character, so the surface that we're trying to array to. And we take our position, so our pos in midair over here, as the position that we want to array from. And then we feed it our hit prim and hit prim UV, which are essentially going to store the primitive number that it finds and the parametric coordinates on that primitive of where the sort of minimum distance was. So if it lands in the square in the middle of one primitive, then the hit prim UV will be 0.5, 0.5. Okay, it's a vector 2. Okay, in this case it's a vector. It does store all three values, but the third value will just be 0. Okay, and then once we've done that ray, the ray just returns a value for the which primitive and where on that primitive the ray is sort of hitting. But we haven't actually gathered that and set that as our new position. We have to manually do that. So we use the prim UV function, which works very well with XYZ dist. So what this does is it takes our hit prim and our hit prim UV and then lets us ask for a particular attribute value at that primitive and at that primitive UV site. Okay, so in this case we're asking for P, which is point position, and setting that as pos. So in this way, this line here is essentially saying where the ray hit, I want you to move your position to that point. Okay, and then we're doing the same thing with the normals. We also want to gather the normals from the surface because we had a normal already, but that's the normal of the original point, same as how we had the original point position stored. But now that we've moved and rayed, we want to set a new position and a new normal so that the next time we loop, when we calculate our tangent is based on the new position on the surface, not the original. And that's where we're going to now kind of create that spiral. Otherwise, every single iteration would just move in the same direction because our position and our normal would be the same. Okay. So now that we've rayed onto the surface, all we need to do is add a point at that position. Because don't forget, this pos is just a variable. It's just a vector. It's a theoretical position. But there exists nothing at that position. We have just been moving a variable, okay? Moving a vector. But what we want to do is represent that vector with an actual point. Have a point exist at that point in space so that it forms something that we can visually see. And so we're adding a point, okay? Add point into our incoming geometry. So that's 0, but we're adding it to pos, which is now our new altered position, okay? Which started as v at P, but it has been altered by our tangent, our offset, and then the ray function. And now, because we add a point at that position, we now have, so we've added a point to our spiral, we're going to append it to our array. So now our array has 2 points in it, the original point and this new point that we've created, which is a little bit to the right and a little bit down from where the original point was, but it's still on the surface. And then we're also going to set its color, the new point's color, to be equal to the color of the original point, because we want the whole spiral to sort of inherit that one color. Because remember, we created that sort of color, and then as it spirals, you want to actually see this whole purple line is 1. Okay. This then, everything we just mentioned loops, and it loops multiple times, right? So it just keeps looping, keeps looping. So we have this happening even here on the floor. You'll see that once it moves along the space and actually finds that the floor is nearer to it than the than the character, then it actually reaches out and rays itself onto the floor. So we end up with this kind of cool stuff happening here where it's reaching from the hammer out to the floor. Okay. And we'll see, we can figure out how many. I mean, I originally had 200 iterations. I'm not sure whether that makes much of a difference because at a certain point, it's just going to keep spiraling around in a circle. okay, because the tangent will then move, but then it rays back onto the same point, okay. Now, once we've gathered all of that, done all of the iterations, we will have a whole lot of points added, but they'll be separate from one another, right? So they will just they'll essentially look like this. Okay, so all of these points, but how do we know which points belong together to be kind of joined into one line? Well, we're gathering an array of point numbers, and so we just feed that array into the add prim function so that it knows which points to add together to form that polyline. Okay, and so we now end up with these spirals. Okay, so that's all that's happening in here. Very simple, but obviously much more simple in Vex than if we had to try and attempt this in VOPS. Okay. Now we're just resampling that, and here we're adding the noise at the top. So I was just adding a noise and kind of just flaring out at the top just to create something a little bit more, fun and artistic. And then I'm polywiring it and faceting it, right? Which I'm not going to click on because it takes a little while to kind of cook that. So, but yeah, you can see here's our spirals. And, if I go and select sort of maybe just like one individual line, you can actually see as I move over them, as it highlights those lines, you can kind of see the path that line is forming. And as it starts at the top and then it spirals around because we keep altering our tangent and normal based on what we ray from the surface. Okay. And some are actually following really cool paths. They end up going all the way down the hammer and then onto the ground. Like that one's like really cool. Okay, so that's how you do it. So I hope you enjoyed this and found it really, really useful. And now we'll move on from vectors.